There's the two different ways that you can make an error. A type 1 error is when you reject H0 when it's true. Type 2 error, you accept H0 when it's false. The approach in statistical testing is to set up the acceptance region alpha so that the probability of alpha is some small value. 0.05 or 0.01 are usually the chosen values. The predetermined value of alpha, 0.05 or 0.01, is called the significance level of the test. It's the probability that the test makes a type 1 error. The critical region should consist of all value of the test statistic that indicate HA is true. H0 should be rejected. The size of the critical region should determine the probability of a type 1 error, should be alpha. And the usual choices for alpha are 0.05 or 0.01. To find the critical region, you find the sampling distribution of the test statistic when H0 is true, then locate the critical region in the tails, either in the left tail or the right tail or both, depending on which indicates H0 is false. We'll be giving examples where they're located. The critical region is split up into the two tails and where it's just in one of the tails. The size of the critical region is chosen so that the area over it, when H0 is true, is equal to alpha. The Z test for proportions, testing the probability of success in a binomial experiment. So you have a success failure experiment. It's repeated n times. Probability of success is P is unknown. We want to test whether P is equal to P0. P0 is some specified number against the hypothesis P not equal to P0. The test statistic, you repeat the success failure n times. You record the number of successes. You change that to the proportion of successes. That should be close to P. In particular, if P naught is the correct value for P, it should be close to P naught. So if this proportion is close to P naught, the null hypothesis of P naught should be accepted. Otherwise, it should be rejected. So to decide whether to reject the null hypothesis or not, the test statistic we use is P hat, standardized when H0 is true. When H0 is true, the mean of P hat is P naught. The standard deviation of P hat is P naught 1 minus P naught over n. So this statistic will have a standard normal distribution if H0 is true. Z should be close to 0. Should have a standard normal distribution. So if HA is true, we expect PZ to be either a large positive value or a large negative value. There's the standard normal distribution. This describes how Z behaves when H0 is true. In here, we accept H0. Out here, we should reject H0. The acceptance region. The acceptance region should be chosen so that the chance of falling in the critical region is equal to alpha. So alpha over 2 in this region, alpha over 2 in that region. That means that these points here, this should be minus sets of alpha over 2. This would be plus sets of alpha over 2. This number is found in a table. It'll depend on the value of alpha. With this choice, the chance of accepting H0 when it's true will be equal to 1 minus alpha. The probability, the chance of rejecting H0 when it's true will be equal to alpha. So accept H0 if Z is between minus sets of alpha over 2 and plus sets of alpha over 2. Reject if it's outside of that region. With this choice, the chance of a type 1 error, chance of falling in the critical region when H naught is true is equal to alpha. So, summary. The test if P is equal to P naught against the alternative P not equal to P naught. We decide on the value of alpha. We collect the data, compute the test statistic. There's the test statistic. It's P hat minus P naught over the standard deviation of P hat when H naught is 2, which is square root P naught 1 minus P naught over N, and make the decision. Except if it's in between these two values coming from the table, reject if it's outside of that range. Example, suppose in the last provincial election, 8% voted Liberal. The party is interested in determining a survey to see if that percentage has changed. So it takes a sample of 800 voters. So basically, we want to know if P is the same as last time, 0.8%, 0.08, against the alternative P not equal to 0.08. We decide on our probability of a type 1 error. We'll choose 0.05. We collect the data. In the sample of 892 are going to support the Liberal Party. If we look at that proportion, that's 11.5%, which is above 8%. Question is, could have that occurred by chance? You compute the value of the test statistic. This adjusts P hat as though it was coming from a distribution centered at P naught with standard deviation, square root P naught 1 minus P naught over N. It turns out to be 3.649. You make the decision, look up Z.025, that's 1.960. We would have accepted if Z was between minus 1.960 and greater than 1.960. We would reject if it's outside of that range. It's outside of that range. So the decision would be to reject H naught. Conclude that P equal to 0.8% is false. There is a significant difference. You qualify the significant difference with the probability of a type 1 error in the proportion of voters supporting the Liberal Party in this election than in last election. A review. This is the two-tailed Z test for proportions. We're testing whether the probability of success in a binomial experiment is equal to some value. So the null hypothesis is it is equal to the value. The alternative is it's not. There's the test statistic, P hat minus P naught, sigma P hat minus P naught, square root P naught, 1 minus P naught over N. There's the acceptance region. The boundaries of the acceptance region and the critical region, they're found from a table. With this choice, the chance of a type 1 error rejecting H naught when it's true is equal to alpha. There's a graph showing the distribution of Z if H naught was true. There's the acceptance region and the critical region. The chance of falling in the acceptance region when H naught is true is equal to alpha. That's what's called a two-tailed test. The critical region is split into two tails. Suppose we wanted to decide between these two statements. P is less than or equal to P naught. Alternative P greater than P naught. The success rate is, the alternative says the success rate is higher than the value of P naught. The null hypothesis, it's not higher. It's either equal or less than. You call the alternative a one-sided alternative. In the other cases, when P was not equal to P naught, the alternative is a two-sided alternative. There's the test statistic. It's the same as before. If H naught is true, we're going to expect that to be close to 0 or negative. If H naught is false, if P is equal to P naught, we expect that test statistic to have a standard normal distribution. If HA is true, we're going to expect the test statistic to be a large positive number. So there's the distribution of Z when P is equal to P naught. Out here, we should reject H naught. Around 0 and negative, we should accept H naught. So there's the critical region. It's located entirely in the upper tail. All of the value of alpha is in the upper tail. The point here is Z sub alpha. For different values of alpha, you can find that value in the table. In tables, out there, you reject H naught. 0 or less, you accept H naught. With that choice, the chance of accepting H naught when it's true is equal to 1 minus alpha. The chance of rejecting H naught when it's true is equal to alpha. So you accept if it's less than or equal to Z sub alpha, reject if Z is greater than Z sub alpha. The critical region this time is called a one-tailed critical region. And with this choice, the chance of making a type 1 error is still equal to alpha. Example, you have a new surgical procedure. It's developed to correct heart defects in infants before the age of 1 month. Previously, the procedure that was used did this successfully 91% of the time. You want to prove that the new procedure is better, that the new procedure has a success rate greater than 91%. To do this, it's been performed 200 times. The null hypothesis is that it wasn't greater than 91%. It's equal to 91% or possibly even worse, less than. What we want to prove is that it's greater than 91%. P is the success rate of the new procedure. These are the two decisions we want to make between these two hypotheses. If this was the conclusion, we would probably abandon the old procedure and use the new procedure. So we choose a value for alpha, 0.05. We collect the data. In the data, 187 cases were successful out of the 200. The success rate is 93.5%. Is that evidence to show that the new procedure is better? This could have occurred that high just by chance. So the test statistic, P hat, which was about 93.5%. P naught is 91%. We compute the test statistic. The test statistic is 1.235. We make the decision. We look up Z.05. It's 1.645. We would only conclude HA, reject H naught, if the test statistic was greater than that. It's not greater than that, so we accept H naught.
I have a question.
Sure.
So wait, why did you pick alpha equals 0.05?
That's a usual choice. I'll make an error. I will make and declare the null hypothesis false for only 5% of the time. If I thought a type 1 error was more serious, I would choose a smaller value for alpha, 0.01. So I only make an error 1 out of 100 times.
Okay.
So here I've accepted H naught. I haven't rejected H naught. 5% of the times I would have rejected H naught when it was true. This time I've accepted H naught. So we can't conclude that H naught, we conclude that H naught is true. More precisely, we can't reject it. There's no significant increase in the success rate over the new procedure. The new procedure could be more successful. It had a slightly higher success rate, but that could have occurred by chance. It's like in a jury trial, you have to have 12 out of the 12 jurors to vote guilty before the person that's declared guilty. That procedure can make a mistake, can actually make a mistake and declare a person innocent when he's actually guilty. But the way one treats that, when a person is declared guilty, you haven't proved innocence. You simply haven't been able to disprove innocence and reject it. So when a decision is made to accept H naught, one should not conclude that we've proven H naught. This is because the probability of a type 2 error could be quite high. Accepting H naught when it's false. If you accept H naught, you could have made a type 2 error. That could be quite high, and that should actually be calculated in order to qualify your decision to accept H naught. So in the Alexa, there's no significant increase in the success rate over the older procedure. You haven't been able to prove the new procedure is definitely better than the older procedure. So maybe at this point we'll end. And I'll just make some comments about when you use a one-tailed test and when to use a two-tailed test. It depends on the alternative hypothesis. The critical region is the values that indicate HA. If only the upper tail indicates HA, then it's a one-tailed test. If both tails indicate HA, it's a two-tailed test. Quite often the research hypothesis is the alternative hypothesis. For instance, you're trying to prove that a new procedure is better. The alternative will be that. Null hypothesis is that that's not true. A drug is effective in reducing cholesterol. There's no change in political opinion at the time of the current survey. That's the null hypothesis. The alternative is what you're possibly trying to prove. So maybe we'll stop at that. And if there are any other questions, I'll be glad to answer them. So in statistical testing, you have test statistic. You have to find that test statistic. That test statistic is usually given. You have to find the critical region and the acceptance region. The size of the critical region will determine the probability that it makes a type 1 error.
I have a question.
Sure,
Isn't the size of the critical region always alpha?
yes. But if you choose a large value of alpha, then it will be a large critical region. Suppose you chose alpha equal to 10%. If you choose it equal to 5%, it'll be a bit smaller. If you choose it equal to 1%, it'll be even smaller still.
So in test questions, will they give you the value
Yes,
for alpha?
yes. And
Okay.
if the value is not given for alpha, the common approach, this is true in research, is to use both alpha equal to 0.05 and 0.01. So if the value of alpha is not given, you do it for both 0.05 and 0.01.
Okay.
Okay, so we'll stop at that point.